Hello, everyone. So there's a lot of quite a few questions on this problem here from the lab. So I figured that I would go ahead and work through it myself, sort of, uh, and show you how you would go about solving this, and some important things to note. There's also going to be some slightly bizarre behavior inside of the actual pipeline or inside of the schedule for these instructions here that is not super obvious, but hopefully I'll be able to clear it up while I'm working through this. So the first step here is going to be to isolate all the dependencies. All the dependencies that might eventually cause a hazard in the pipeline and cause things to have to be delayed. We want to figure out what all of those are. So here we have just essentially the normal pipeline with IF, ID, LD, EX, and ST. So, and as it says here, you need to do the IF and ID stages before any dependencies are detected. Obviously, I mean, here we know what these instructions are, but the idea is that at runtime, we don't necessarily know what these instructions are until they've been decoded. Right? All we know is that there's just some set of instructions somewhere. We're going to read the first one, fetch it, decode it, and then run it. And so we need to be able to fetch and decode it before we can figure out what the dependencies are and handle them. So that's something we're going to have to keep in mind later on. So for dependencies, we'll look at the instruction letter here. So I'll just use A through F. And we want to find which units specifically the dependencies are between. So just a small note here, add R1, R2, that is R1 plus equals R2, essentially. So the destination is on the left-hand side and the source or whatever is on the right-hand side. So here, obviously, we can't have, A does not depend on anything. I mean, if there were instructions beforehand, there might be some dependencies, but in this case, there's no instructions before, so we'll just say that it has no dependencies. B, well, we might need to use the result of A somewhere. So here, remember, this is R1 plus equals R2, which means we have to know what R1 is before we can add R2 onto it, which means there's going to be a dependency between reading this value of R1 and when it gets actually written to in this previous instruction. So now we know there's going to be a dependency between B and A, and now we need to figure out exactly when that dependency occurs. So here, this add is going to occur in the EX stage of the pipeline. And this move here, this is moving from memory into a register. So that's going to be a load operation. So that's going to occur in the load unit. So here we can describe that as saying that the execute of B, maybe put a dash there, depends on the load of A. And you can pretty much write these down. However, I'm just going to use this. So this depends on this. So R2 isn't used beforehand, so that's good. And technically, there's also a dependency in writing to R1 because we're doing R1 plus equals R, but this dependency here handles that. So we're good for B. For C, we're taking the value of R1 and putting it into this location in the memory. So here, the fact that we're taking R1 and putting in this location means that we need this when we store, right? So this R1 value is going to get into the memory at this location during the store phase because that's storing to the main memory. So we know here that the store for C is going to depend on the execute of B, because the execute of B is where this R1 value is going to get updated. And then we want to use it again in this instruction here. So in order to be able to move it, we need to be able to, have the value. So that's the dependencies for C. Going on to D, we can see that we're reading R0. And here, it's important to note that here you're also reading R0. So you need to be careful with that and see if there's any dependencies with anything being used to access in the main memory. And just as a quick tip here, if you're still not entirely sure about how memory works, memory is just an array because, really arrays are modeled off of how memory is structured. And so it literally just acts like an array. You can just think of memory as we have this array, I'll just call it mem, and it has a massive amount of locations. It's like maybe an array with billions of elements. If you have like gigabytes of RAM, that's going to be billions of locations. And so when we see 100R0 like this, all that is really saying is access the memory array at the location, at the index 100 plus whatever R0 is. That's literally all this means here. And if, let's say, we just had, so this is essentially, the same thing as when we write 100R0, right? And you can even think of these brackets as sort of being the index into the memory, right? Instead of calling them indexes, we call them addresses. But it's pretty much exactly the same thing. So if you're having a little bit of trouble with the memory, just think it's an array, and that is entirely accurate. So this instruction here is essentially saying memory at 200 plus R0 equals R1. And because of that, essentially we have to read the value of R0 in order to know what index we're using into the memory, or what address we're using in the main memory. And so here there's potentially a dependency with R0. But since we're reading R0 here and we're reading R0 here to figure out what the memory location is, that doesn't cause a dependency. So now with D, so we're reading R0, that's fine. In this add here, because again, this is plus equals, so this is actually 200 R0 equals 200 R0 plus R0. And so here, we're both going to read this memory location and store to this location. And so this actually is going to use all three of these units, LD, EX, and ST, obviously IF and ID. Because we need to first load this value from memory, then add it to this register, and then store it in this. And that addition there occurs in the execute stage. So here, the only dependency we have is in C, we write to this memory location, and then we want to read it right here. And then after we read it, we'll eventually overwrite it. So we don't really need to care about the overwriting as long as this dependency is satisfied. But this means that for the load for D, that's when this value is going to get read, depends on the store for C. And otherwise, we might be reading two different values in the main memory. Then that's pretty much it for the dependency, because technically you could say the store for D depends on the store for C, because we're going to be overwriting this value, and we don't want to overwrite the value here until this value is overwritten, right? We want these to occur in the right order. But since we already have this dependency, this is sort of redundant, because the store for D is always going to depend on the load for D, just because they have to execute in that order, right? The load has to happen before the store. So this dependency occurs. Because this dependency occurs and this dependency occurs, this one is just natural in the pipeline. And so we don't actually need to write this down, because if we make sure that this is true, this is satisfied, that this happens after this does, then this will the other dependency there will also happen. Okay, so now we go on to E. So E here, we're going to be loading from a new memory location into R0. You might think there's no dependency here, but the problem is that we're updating R0, and in this D operation here, we're using R0 for everything. We're using R0 for everything. Right here we have 200 R0 equals 200 R0 plus R0. And so during the store phase, when we're actually going to put it in here, we need R0 to be able to compute this address in the memory, to compute that index into the memory array. If we don't have R0 and it's not the correct value, then that doesn't work. So we actually have that the load of E depends on the store for D. So the load for E depends on the store for D. And that's because, well, when we load here, it's going to completely override R0. And that's used consistently throughout this instruction here. So if we don't make sure that that is satisfied, it's going to screw up our computation. And that's pretty much the only dependency here, because this is a completely new memory location that hasn't been accessed before. And then finally, we have R2 equals R2 plus R0. So technically, there is a dependency between F and B, because here we'd be overwriting R2, and here we're reading it. But those are far enough apart, right? This is 5 instructions apart, and the pipeline only has 5 stages, so that's fine. You do need to watch out, though, for dependencies that go a bit further back, like F and D, F and C in some cases. But like if you see R0 here and R0 here, meaning that there's a dependency between these two, there's not really any reason to check for a dependency beforehand. But again, it's not a bad idea to just mark down every single dependency that you see. Worst case scenario, you just wrote down a little bit of extra stuff, and then when you're filling out the pipeline, it's a little bit of extra stuff to check to make sure that it's satisfied. But here, we do need the value of R0 that is written, that is loaded in here. And we're going to be using R0 in the execute stage. So the execute for F depends on the load for E. And these is pretty much all all 5 dependencies that might cause an issue. Okay, so now we want to figure out how stuff is moving through the pipeline. So the first thing I'm going to do is I'm going to actually draw out a symbol, like symbolically draw out this pipeline. And we're going to literally watch stuff as it moves through, because that'll really help to understand what happens specifically with this E, D, E, and F instruction. There's some sort of bizarre behavior that seems to happen when we're drawing out the schedule. But if you look at how the data is actually flowing through the pipeline, it ends up being pretty obvious. So here we have IF ID, LD, then EX, and then finally ST. And here, I'll just write like A down here. That just means the A is inside of the IF unit. And then we can also just draw out our schedule here. And here the problem does specifically say that it's 3-way interleaved memory, but since there's only 3 units, I'm not even going to bother marking anything, because if it's 3-way interleaved memory and there's 3 units using memory, obviously any number of those units can be used. So we can just ignore that because it'll be fine. So a couple of things about pipelines that I just want to quickly mention. So the oldest thing in the pipeline essentially has priority. So the CPU doesn't really want to just start a whole bunch of new instructions if it hasn't finished older ones, right? It doesn't want to just keep older instructions in the pipeline, just stalling things, just sitting there doing nothing. It sort of wants to give priority to the older instructions so that they can be out of the pipeline and the CPU can start processing new things. And so when you're looking at the instructions and how they're processing, you really do want to look at making sure that older instructions finish first. So we'll start off with this first cycle here. So at this stage, right at the beginning of this program being run, the CPU knows absolutely nothing about any of the instructions. It doesn't have a single clue about anything that's going on, what the program's trying to do, anything like that. So the first thing that it's going to do is it's just going to start by fetching the first instruction. So we sort of see A come into the pipeline, and it's going to sit in this IF unit. So we can go ahead and write that down. So A is going to start right here in the IF unit. So that's pretty much it. It just fetches it. It still doesn't know what A does. It has no clue what's going on with A at this point. So now it's just going to go ahead and move on. So it's fetched A, and it knows that that's fine, right? It can just move on to the ID unit. And when it does move on here, B is going to start and go ahead and get fetched. So we can go ahead and write this down. So A is in the ID unit, and B is in the IF unit. That's pretty much it. So now, at the end of this cycle here, right at this point in time here, so this is cycle number 1, cycle number 2 is this whole box here. Or you could say that maybe this line here is the end of cycle 1, and this box here is the end of cycle 2. It doesn't really matter. But right here, once A is done in the ID stage, the CPU now knows exactly what needs to happen for A. And it can start planning things. But it doesn't know what B's doing yet. All it has done so far is gotten the literal binary for the instruction from the main memory. And it still needs to figure out what that instruction's doing. So here now for A, we should probably take a look here at what units it uses. So here, it's just going to be performing a load. It's just going to take this value here and put it in that location and in that register here, and that's it. It doesn't do anything else. It doesn't need to execute or store anything. So it's just going to be using the load unit. And so A here is just going to use the load unit. And I'll just mark that down there. So now the pipeline will just intelligently make A go to LD, and then after that, it's done. So it'll just remove A completely from the pipeline. So in the second stage, on the third cycle here, we'll see A move on to the LD stage, B is going to move on to the ID stage, and then we'll start fetching a new instruction. So A is going to move on to LD, B is going to move on to ID, and C is going to start getting fetched. And at this point, we're good, right? We've at the end of this stage here, we'll know exactly what is going on with B, and A is going to be finished, and C we've just sort of fetched the instruction. So now that we've decoded B, that's when we need to start paying attention to the dependencies, because I mean, before we've decoded B, we have no clue what's going on, and it's not going to know about the dependency. And so once that B is decoded, well, then we have A decoded and B decoded, which means the CPU can figure out what the dependencies are. And there's essentially just an algorithm, a hardwire circuit on the CPU that figures out what dependencies are and will fix them and handle them however that it's done. That's done. So at this stage here, it sees that the execute for B has to happen after the load for A. Well, the load for A literally just happened. So the CPU actually won't even mark this as a dependency because, or as a hazard actually, because this dependency is already satisfied. So we can actually just, for our purposes, we can just check this off. And we know that we can just continue processing B, completely ignoring everything else, because all of its dependencies have been satisfied already, because A is done. So now moving on to the next stage. Well, actually first we should figure out here. So instruction B here, now that we've decoded, what units does it use? Well, it just uses the EX unit because it's just doing an addition between registers. So B here is just going to use EX. And as we just figured out, there's no dependency between A and B, and A is just going to leave the pipeline now. So B can just move ahead to the EX unit. So A gets out of the pipeline, B moves on to the EX unit, and then C is going to move on to the ID unit, and then D is going to go ahead and start in the IF unit. And so that's what's going to be going on in this next cycle here. So we have D in 4, D in the IF unit, C in the ID unit, and B jumps up here to the EX unit. And that's also the way that I did that there is I looked at first the rightmost instruction, I figured out where it goes, then I go on to the next instruction and figure out where it goes. But it can't go past, like if A had stopped here in the EX unit, then B can't suddenly go through through instruction A. It's sort of blocked. So C can never go in front of B. It's sort of blocked by traveling, right? You can sort of just imagine C moving, it's blocked by B. So it couldn't move past it. So we're here. So now we're decoding C. So now we figure out what C does. C here is just a store. So it's just going to end up using the ST unit. And we see here that there's a dependency between the store of C and the execute of B. But at the end of this cycle here, B finished executing. So this dependency is automatically satisfied. And again, the CPU wouldn't actually even mark this as a hazard because it would know internally, because it's decoded B and C and started executing them, that B is going to be done by the time that C needs that result. So the dependency here is satisfied, and we can just keep progressing as usual. So B here is done because it used the execute unit and now it's done. So it just, goes out of the pipeline. C needs to use the store unit, so it can go ahead and just go straight to the store unit. There's nothing blocking it, so it can just progress straight through these units here. And it's worth noting that, in a very simplistic pipeline, the instructions would just move forward one unit every single time. But it's not too difficult to just add a little bit of logic that says, well, if you don't need the LD unit, you can just go straight, you can just skip it and go straight to the EX unit or so on, right? So C here just goes straight to the ST unit, and D moves on to ID to get decoded, and we can go ahead and start executing or fetching instruction E. And the idea here is, if the fetch unit is free, we may as well just start fetching a new instruction, right? If the further ahead that we know about things, the better, because ideally then the CPU can more intelligently schedule things. So the more information it has, the better. However, it does have some restrictions, right? It can't have multiple things in the IF unit, at least not with this pipeline. So yeah, so we progressed forward, and now this tells us exactly where everything is in the next stage. So here we have E in the IF unit, D in the decode unit, and C just goes straight to the store unit. Okay, so now we have instruction D. So instruction D here, again, has to load this value, add R0 to it, and then store it in this memory location. So it actually has to use all 3 units. So LD, EX, and ST. And we have the load for D is dependent on the store for C. Well, again, the store for C is just finished happening at the end of this cycle here. So that means this dependency is going to automatically be satisfied because obviously C is going to be done in the ST unit before D has to do literally any of these units. So that dependency is satisfied, and we can just progress forward as usual. So C is done, so it'll move out. D will move forward to the load unit. E will move forward to the ID unit, and F will go ahead and start getting decoded. So it's important here to think, I mean, normally, like if you're working on this problem, you might just write out A where it goes, and then B where it goes, and C where it goes. But really, that's not what's internally happening. In terms of solving these sorts of problems, it's definitely a good shortcut to take. You can simplify the work, especially if you're not drawing this sort of thing out. But really, everything happens one cycle at a time. And the CPU figures out exactly how everything moves every single cycle. It doesn't, pre-schedule things ahead of time. It figures out what it needs to do as it sort of gets things to work on. So, so everything here would move on. Nothing really new here, right? We just decoded E. So here, we're decoding E and we're loading D. So this is actually going to be the next cycle here. And we just decoded E. So now we need to worry about, the CPU will actually detect this dependency here and figure out whether it actually matters. Well, now we actually need to wait for D to pass through the store unit. So now it actually has to do some delay. So this is the first hazard that we've come across. These are just technically dependencies, right? Because, these do have to happen in the right order. That's entirely correct. But in this pipeline, it turns out that this isn't actually something that it needs to worry about because it's automatically going to be true. You can't generally just assume that, though. It's best to write them out and actually manually check once you get to that point. But here we hit the first hazard. So now it says the CPU figures out, okay, well, I know E needs to use the LD unit, but it can only use the LD unit after D uses the ST unit. So now it's just going to sit in this ID unit until it can go ahead and use the LD unit. So what's going to go on here is the next cycle. D is just going to go ahead and move forward, and everything else is going to stay exactly where it is. But because it's not actually using this unit and it's just sitting there, we're not going to write them down. So here, we're just going to write D in the execute because D moves on and then starts just chugging away at this, doing the addition there. And I should probably write down, once we've just decoded E, this is just going to be doing a load here, right? Taking this value from memory and putting it here. So this is just a load. And that's our dependency here. The load for E depends on the store for D. So D moves on, but these just sort of stay here. So that means we cannot start decoding G, right? Because F is blocking the IF unit. And we can't start decoding F, right? We can't put F here because E is sitting and holding up this ID unit. And so that sort of blocking there is going to prevent anything else from happening in the pipeline before the load unit until E can go ahead and move on to the load unit. So that's why F doesn't move on here. We fetched F, right? Because the CPU just, started a new cycle, saw that it wasn't actively fetching something, and just started fetching a new instruction because it wants to have as much information as possible. It wants to do as much work ahead of time as possible, because if you have to do it later, it's just going to end up being slower. So D goes ahead and gets executed right here in cycle number 7. We haven't fetched anything new now, so we just sort of need to keep going. So that's it for this cycle. Then D is going to go ahead and move on to the store unit, which will be right there. That's during cycle 8. And again, E is waiting until this cycle now is done before I can move on to the LD so that things happen in the right order. So here again, we're not fetching anything new, so we don't have any instructions to handle. We don't have any new instructions being decoded, so we're good. And then finally, now on this next cycle here, D is going to go ahead and move out. And because it just finished it in this ST unit, E can go ahead and get into the load unit. F can go ahead and go into the ID unit. And if we had an instruction G, it would go ahead and get fetched at this point. But we don't have a G instruction here. So now on this next cycle here, we see that F gets decoded and E goes into the load unit. After this cycle, E is going to be done because E only needs to use the load unit. And F here is just going to be doing an execute. And now we have, once it's been decoded here, well, it figures out that it needs to use the execute unit, and it also figures out this dependency occurs, but it knows that at the end of this cycle, E is going to be done in the LD unit. So this dependency is satisfied here. And we also satisfied this dependency here, which did cause a hazard, by just waiting to execute E in the LD unit. So now we know that this dependency is handled, so we can go ahead and just figure out what the next cycle is going to do. So here, E is going to just get out of the pipeline. F is going to go ahead and move on to the unit that it needs, which is the execute unit. And then it would just run this because it needs to do that execute. And again, we're not fetching or decoding anything new. I mean, really, the CPU would have more instructions to execute, and it would start doing that. So there would be stuff going on here. Like if there was an instruction G, it would go ahead and start right here, move on to here, and keep going. But for this problem, it'll just stop there. F will go ahead and get executed. It's not fetching or decoding anything new. And once it's done, it'll be out of the pipeline, and we are done. And this is the solution to the problem. So you do see that there's this weird gap here. But again, that's because F is sort of just sitting in this IF unit and E is sitting in this ID unit, and they're both locking them completely. They're clogging up the pipeline. You can literally imagine this like as a pipe, right? You have something flowing from here to the IF unit, to the ID, LD, EX, and so on. And if at any point in time, one of those things has to stop in the pipeline, it clogs up everything behind it as well. And so, yeah, this is the solution to the problem. If you do have any questions about this, feel free to put anything in the comments and I'll try to get to it. Or if you're actively in the course, you can send a message to one of the TAs either by email or on Discord.